Math.
Yes.
Y'all ready for this? Oh, I'm so glad. Look at this. It's working. We're alive. It's Saturday night. No, it's Monday morning. All right, let's.
You know it's recording this.
I know. All right. Does someone want to read that first paragraph for me, please?
I will.
All right, go for it. Thanks, Sam.
Now that you've seen that there are contexts for continuous exponential functions, it's a good idea to start thinking about the numbers that fill in between the values like 2 squared and 2 cubed in an exponential function. These numbers are actually pretty interesting, so we're going to do some exploring in this test to see what we can find out about these in-betweeners.
Awesome. Thank you. So if we were to look at this equation right here, f of x equals 4 times 2 to the x power. If we have a 0 in for x, it equals 4. Why does it equal 4 if we have a 0 in for x?
Because 2 to
Because
the
anything
zero
except
power
for 0
is
to the 0 is 1.
Correct. Yeah, both of you are right. Anything to the 0 power
Well, anything except 0.
except 0 is just 1. So 2 to the 0 power is just 1.
Yeah.
And then we multiply 1 times 4, and that gives us 4, right? So they filled that in for us. What if we had 4 times 2 to the first power?
It would be 4 times 2, which is 8.
Yeah, very good. What about 4 times 2 to the second power?
16.
Nice, because it's 4 times 4, which is 16. And then 4 times 2 to the third power. It's 2 to the third power.
4 times.
Yeah, 2 times 2 is 4 times 2 is 8.
Times 4 is 32.
Very nice. And then 4 times 2 to the fourth power.
You have
2 times 2 is 8. 4 times 2 is 8 times 2 is 16.
4 is 65.
64, right? So here we've got all these values. The table's filled in. 4, 8, 16, 32, 64. What can you also tell about these values from left to right? Like,
It's
yeah, it's doubling each time, right? Which, if we look at the base of our exponent, that should tell us that it's doubling each time. Okay, so from the previous term, if we wanted to write a recursive equation, we could say previous term times 2 gives us the next term. So the next thing that it wants us to do is plot these points on the graph at the end of this task, okay? So I'm writing this in blue, so I'm going to plot these in blue at the end of this graph, where it was 0, 4, then it was 1, 8, it was 2, 16. Also pay attention to these lines. Each vertical line is actually 1/2, not one whole. So just be careful about that. Make sure you're plotting carefully.
2
16, 3 is 32. And then 4 was 64.
yeah.
Way up yonder.
So it's exponential.
It is exponential, and we can tell that because there's the exponent that is the variable, right? That's part of the definition of an exponential function. Okay, so let's say we want to create a table with more entries, maybe with a halfway point between each of these points in the table listed above. There are a couple ways that we might think about it. We'll begin by letting our friend T. Ravis explain his method. So T. Ravis makes the following claim. If the function doubles each time x goes up by 1, then half that growth occurs between 0 and 1/2, and half the growth occurs between 1/2 and 1. So for example, we should be able to find the output at x equals 1/2 by finding the average of the outputs at x equals 0 and x equals 1. So I'm going to plot this one in green. It says fill in the parts of the table that we've already computed, then decide how we might use Travis's strategy to fill in the missing data, and then we'll also plot Travis's data on the graph at the end of the task. So we've already filled in which values? What
2,
did?
3, and 4.
Yeah, 1, 2, 3, and 4. So let's just go ahead and fill those ones that we've already computed. Like that. Do you think I can charge this well? through this?
I mean, you should be able to. It's just a matter of whether the dongle thingy supports it.
It's just called a dongle, Tyson.
Right?
The dongly thingy. Let's see. Let's find out. It did it. Snap. All right. So then how can we can use Travis's kind of idea to figure out 1/2. What was his idea? What was his idea?
If the
Okay.
function doubles each time x goes up by 1, then half that growth occurs between 0 and 1/2, and the other half occurs between 1/2 and 1.
So how do we compute that?
You'd have the growth and then add that to the previous term.
Okay. I hear that. So you half the growth, and then you add that to the previous term. So that's not exactly what he said, but I think it'll work. It's the same idea. So it would be plus 4 in this one. So we take half of that and we say 4 plus 4 divided by 2, which is 6, right? 4 plus 2. Travis's idea, though, is this thing highlighted in green right here. It's taking the average of the outputs of the x equals 0 and x equals 1. So if the outputs are 4 and 8, to find x equals 1/2, we can do 4 plus 8 and then divide it by 2. Take the average. So what's 4 plus 8? 12. And then divide that by 2? 6. So actually it works the same way as Tayson's did. But this is kind of more his exact strategy. So then if we do that same thing up above the 3/2, we go 8 plus 16 divided by 2. What's 8 plus 16?
I don't know.
24.
24. Very good, Bill. 24 divided by 2 is?
12.
12. Nice. And 16 plus 32?
54 or something, I don't know.
Yeah.
Close.
52. I don't know.
Close.
51.
48. Not that close. Okay. Nope. Oh, 48. And then divided by 2. Sorry. Tee. What's 48 divided by 2?
12. Wait.
24.
24.
48 divided by 4 is 12. All right. And the last one, 32 plus 64 divided by 2. That's 96 divided by 2. 48. There's the 48 that we wanted. Okay, so there we've got these points.
Doubling too. That makes sense. But
The halves are doubling. We think it makes sense. Okay.
the interval of 1, it's going to double regardless of where those points are in terms of even or
Okay.
either integers or decimal numbers.
Integers or or decimally numbers, yes. Okay, so let's plot these points on the graph as well. I'm going to plot them in green this time.
Or
So this is 6.
so
Did I? Oh, I plotted that first one incorrectly. Should be 8, and I plotted it at... Oh, no, I plotted it at 8. Nice. 6.
no, that's right. It's 1/2. Oh wait, 1/2 is 6.
Mm-hmm.
Yeah, that's right. It's half of 1.
Hold on. No, look at this. 5, 6, 7, 8, 9, 10, 10. That's why.
6, 7, 8, 9, 10.
Look. Oh. Oh no. I see it now. Okay, my bad.
It's right.
Sorry. Oh, that's great. Can't wait to put this on YouTube. Oh, all right, great. That red was very confusing. Okay, now we're at 6. And what's the next one? 12? No, this one's at 12. And then it's at 16. And then we've got 24. Shiminy Christmas, man. Whew. So when's my surgery? It's on Wednesday, Thursday?
Needing help with his math homework.
He's going to be like, this dude does not know what he's talking about. And then 2448 is the last, or is the next one, 40.
The kind of thing that's going to show up in like 12 years randomly.
Yeah.
When I grow up.
It's like, what are they talking about? Local math teacher cannot count. It's awesome. Okay, so we've got all those in-between values, the in-betweeners. Points in green. All right, nice. Oh, brother. Okay. What are your thoughts so far on Travis's idea?
It's good.
Okay, we think it's good. How does it compare to the table generated in problem 1? Like if I were to put a ruler right here and draw a straight line,
So I don't think it is entirely correct, but I think it's definitely close.
okay, definitely close, but not entirely correct. What's your reasoning behind not thinking it's entirely correct?
Okay, because if you look at the first part, like let's say the first half of this current line and the second half of the current line, the rate of change is drastically different. And his whole thing relies
it's
on
like
the first part of the
up
point.
more.
It have changed in the first half and the same in the second half. And I think it's going to change more in the second half than the first half.
Okay.
But it's going to follow the same pattern.
Yeah.
An actual greater curve.
Yeah, well said. Okay, so right now we've got this straight line that goes from the point at 0 to the point at 1, the straight line from 1 to 2, 2 to 3, and so on, right? But didn't we say this is an exponential function? Are exponential functions straight lines? No. Yes, it's just like that. It's a curve, right? So by the fact that I was able to connect these straight lines, we know something might not be right. Yeah.
I mean, it's definitely not a bad visual analogy, but it's
Not a terrible linear or visual analogy, but you're right, it's linear, right? So this would work, this line of thinking, see what I did there? This line of thinking would work if it were a linear function. Come on, that was funny. Linear line of thinking?
okay. So
Guys.
I didn't.
Boy, Jimmy, not struggling with
I
math.
didn't
Fuck
realize
those
you said that.
So Travis' idea, it would work. It's saying for what kind of function would this work? It would work, like Sam said, if it was linear. A linear function. But we know that something's not right. Oh, can I? How do I? Yeah. Oh, no, hold on. This is very important. Dang it. I forgot how to add things. Oh, there it is. Dee. Just gonna delete that one
Maybe
and
we
delete
should
that
end
one.
this video.
I appreciate your input. All right. Miriam suggests.
Gotta get that thinking emoji.
This is going to be wonderful for that one time in like 5 years when you have to take a sick day and you just post a link to this video and like no one will understand anything.
They're going to understand it. It's just going to be a lot of fast forwarding. Okay.
And a lot of emails to you.
Miriam suggests that they should fill in the data table in this way. I notice the function increases by the same factor each time x goes up by 1. So she's thinking it doubles in the entire thing. I think this is like what we did last year in geometric meanies. Do you guys remember that lesson at all?
No.
Me either. I didn't do it with you though, that's why. But to me, it seems like this property should hold over each half interval as well. So she's saying that we should have the same multiplier rather than just like it goes up by 2, so the half interval goes up by like the average of that, right? She's saying, no, I think that from here to here, I need to multiply by the same thing as I multiplied to get from 1/2 to 1
Yeah.
so that I can go in that order, right? Rather than just taking the average and adding, which is a linear idea, I need to do a multiplication somehow. Okay, so what we need to do is fill in the parts we've already computed and then try to use Miriam's strategy to fill in the rest of the data. So what we should be doing is getting some constant multiplier to go from one term to the next term each time. Okay, so let's see. We can fill in 1, 2, 3, and 4. So if we fill in, that's 8, 16, 32, 64. Okay. So I need to multiply 4 by something to get me a number that I can multiply by the same thing to get 8.
2.
2? If I multiply 4 by 2, though,
You get 8.
I get 8 right there. And I need to get 8 on the next one.
Got that.
Oh, snap. I should also change my color so that we're not confused on the graph later, on the graph.
You multiply.
So what can I multiply by 4? It has to be smaller than 2,
Yeah.
right?
It has to be like a
It would
half.
have to be smaller than 2. It would also have to be right around 1. Like it couldn't be 1, but it would have to be like 1.25 or something.
Okay, so it has to be bigger than 1, less than 2, so 1.25-ish. Let's see.
You're grabbing branch practice for a second.
No. I'm looking for a calculator. There's one. So if we multiply 4
It's going to be greater than 2.
by 1.25, that gives me 5. Okay, and if I multiply it by 1.25 again, gives me 6.25 instead of 8.
What if you do? Wait, did you do 1 and 1
So
fourth?
then
Or did
1.25 is 1 and 1
So
fourth.
do 1 and a half.
Okay, so 1.5. Let's try that. So 4 times 1.5, that gives me 6 times 1.5, that gives me 9. So that one's too big.
1/8. What's 1/8 and this one?
Well, that's smaller than 1/4, right? This one's too small.
What's in between 1/4? 1/3.
third, you've got
So like let's say 1.33. So 4 times 1.33, that's 5.32 times 1.33. That's 7.07. So we're still a little too small.
1.4.
1.4, too small. Okay, 1.4, so 4 times 1.4, that's 5.6 times 1.4. Oh, that's closer, 7.84. So still just a tiny bit too small.
1.5?
I think
No, we already did
that's
1.5.
going to be a decent part of the
6.
problem.
1 point.
Is that exponential
4,
functions are going to go through every
2.
single number, right? In terms of that curve, so
True, so one,
finding a half may seem like it
4.2.
would be a nice whole number for us. It might be
What was it?
like some irrational number you'd have to multiply by in order to get exact.
oh, so an irrational number.
So
Huh. Okay, what kind of, so, sorry, I want to come back to that thought in just a second. But I've got 4 times 1.42, that got me 5.68, and then times 1.42 again was 8.0656. So we were like right there.
I think you
Right?
have to keep fine tuning it down and down and down and down.
1.41.
Okay, so 1.41, yeah, fine tuning it down and down and down. So 1.41, 5.64 times 1.41, 7.95. So now we're a little bit too low. So we would have to go like 1.414 or 415 or something, right?
Yeah.
But I want to talk about what Tayson just said. He just said something about a irrational number, right? We're thinking about rational numbers, which are decimals that end or can be represented as fractions, right? So like even 1/3, it goes 4.33333, whatever. It goes on forever, but you can represent it as a fraction.
As a repeating pattern.
Yes. What about what are some examples of irrational numbers?
Square root of 2.
Square root of 2, that's a great example, right? It continues going on. When I put the square root of 2 in my calculator, it gives me 1.414213. That sounds really close to what we just had, doesn't it?
Yeah.
So what if I multiply 4 by the square root of 2? What do you think? 4 times the square root of 2, that's 5.656854294.9. But what if I do it by the square root of 2 again?
Is it 8?
It's exactly 8.
How the heck?
So that is exactly 8.
Yeah, irrational numbers are funny in that they go on infinitely, but you can add them together to a non-infinite number.
You can add them together or you
Like,
can multiply them,
yeah,
right?
multiply.
Yeah, so you can multiply irrational numbers to make a rational number. So when I multiplied 4 by the square root of 2, I got this number. I got 5.65,
Yeah,
and I'm going to just go ... I'll chuck an ellipses right there. But then when I multiplied by the square root of 2 again, I got 8. Which, let's look at an irrational number, because when you multiply two things, you could say 4 times the square root of 2 times the square root of 2, right? What is the square root of 2 times the square root of 2?
would be the square root of 2 times 2, which is 4, which is 2.
Right. So equals the square root, 4 times the square root of 2 times 2, which is 4, which equals 4 times 2. So to get from here to here, we did times 2, which is the square root of 2 times the square root of 2. But that in-between phase, we multiplied by the square root of 2. Right? So up here, it was times 2, and down here, it was times the square root of 2 times the square root of 2. Huh.
So now I'm wondering, is this really something they want a concept for? Because there are definitely going to be numbers where when you square root it, like let's say it increases by 25 every time. That half number would be a nice and pretty number. So why didn't they do that?
That's a good question.
Like, this is just all going to be speculation. Do you think there's something that they wanted us to gain from irrational times irrational, or do you think it's just...
Oh, yeah. This is by design.
Okay.
So let's talk about, or first let's finish filling this in, right? So now I've got 8 times the square root of 2. And that is 11.31 ... ellipses. And when I multiply that by the square root of 2, what do you think I'm going to get?
16.
Yeah, and I get exactly 16. Okay, so now we've kind of confirmed this is the right number, right?
Well, we mathematically justified it by the times square root of 2 times square root of 2 equaling that first.
Yeah, that's a great point. We've mathematically justified it, right? So now we've got 16 times the square root of 2. Let's just keep filling out this table. That's 22.62 ... And then I've got 32 times the square root of 2. That's 45.25 ... Okay, wow. So those numbers are kind of grody, but they are accurate. Because when we multiply them by the square root of 2 again, we get that whole number. Yeah, Haley. Go for it.
Yeah, this comes back to the point of any graph with any slope is going to pass through every number at least once. So
On the x-axis, you mean?
Yeah. on the
Yeah.
axis. So
Huh.
we just managed to find one where that point where it intersects with a nice number is a not nice number.
That's true. It is a very not nice number. Okay, but she says, or they say, let's go ahead and plot these points on the graph. So we're going to try. So The first one is 1/2 and 5.65-ish. So
Rational numbers. This should be fine.
1/2, 5.65-ish. So it's just under 6 where we graphed Travis's, right? And then it's 3/2 or 1.5 and 11.31. So 11.31, just a little over. And then it is 5/2 or 2.5 and 22.62. Oh, wait. The green, yes, 22.62. So we can see that this is pretty consistently like beneath where Travis's was, right? And then 45.25, so now we're at 45. Oh. This one's substantially lower.
Oh yeah, because it's going to get lower and lower and lower.
Okay, so it would get further and further away from that linear function, right? Huh, yeah.
Now it's
So
curving.
that the very first one was incredibly close because the rate of change was so close to linear. But as we get further and further away from linear,
Oh no.
you're definitely not the art teacher.
That you're spitting right now. Those are facts. But you can see, yeah, that has a slightly more of a curve. Wow, that line is. It's got curves all over the place. It is just. It's squiggly. That's what I'll say. It is squiggly. What?
Picasso would like to know your location.
That's good. I like that. All right. So we've got all those points plotted. Excuse me. So now, what if Miriam wants to find the values for the function every third interval? Ooh.
Get you to the square root
Right.
of 3 now?
Yeah, just
Will it be the-
square root over-
Okay, let's try the square root of 3. So
This girl is crazy.
this girl is crazy. How about yellow? Can you guys see yellow? Oh, I could do black. Why not black? Here we go.
Okay, instead of 2 times equaling to 4, we need, wait.
So it's times the square root of
How do
3.
you, like, plug it in a calculator?
The square root of 3?
No,
Or just the
like,
square root?
Wait, I think I can plug it in. So if you do 4
Usually the second key.
Yeah, it's like second, and often it's right above where your squared button is.
is it the one with the X? Or just,
Should be x squared. It should be the square root with the x.
yeah.
No, you want just a regular square root. Because the square root with an x means that you could do something like this. Like the 5th root of x.
I was wrong.
Why would you need to know the 5th
Yeah.
root?
What?
When will you use the 5th root of something?
It's very fortuitous that you asked such a question, Tayson.
Oh.
Because
Oh, so we're not going to go with the square root of 3, we're going to go with like the cubed root of 2 or something.
I'm gonna just write that down over here. And I'm just gonna tuck this guy away for just a minute. Because the 4 times the square root of 3 is 6.92 ...
Okay, so.
And then times the square root of 3 is 12. Just 12. And then times the square root of 3 is 20.78. That is
Not.
too big and ... So that is false.
Okay, so. Yeah.
I mean, I think it's interesting that after 2 of them, it multiplied our input by 3, right? Because it's
Yeah,
the...
'cause okay, so I think that is going to be the proper equation for if you're changing, or if instead of the thirds, make it 0, 1/2, 1, 1.5 for a change of 3.
So,
For a of 3.
okay, so if this was 1 and this was 1/2, then this would function properly, right? And we just pretend like this doesn't exist for right now.
Yeah.
Then that would be right, because if we're tripling this value,
Yeah, you're true.
right, we have 2 jumps. Yeah, so there's 1 jump, 2 jumps. And look, we're taking the square root,
Now,
right?
That's part of the thing. Okay, so there's the 2 numbers, right? I was thinking there's just the 1 number, so we've got to change it for the 3. No, but you have your rate of change, which is what you're rooting, I guess. and then you have what you're rooting it by.
Yes.
Definitely not proper math terms. What you're rooting it by.
Yeah, what root you're taking.
Like radian. Isn't it
Radical?
radical, radian?
Like the radical value, maybe. We'll kind of talk through that more.
Terminology in math
Got
is
your
fun.
It's
radius.
fine. You got you. And your ulna / diameter. Wait.
Okay, so you're going to take something to the
Medical
x
terms.
root, where x is the number, where x is the denominator of the fraction you want, and then
Oh, the xth root, where x is the denominator. Okay, so we're saying gonna put this outside of the radical,
yeah,
and then what would go in here?
that would be your stretch.
That's is it
Or,
your
no, not
stretch?
your stretch, but what's your it is your 0 to 1.
It's the multiplier.
Yeah.
Yeah. So we're going from 4 to 8 is a multiplier of 2. So that's what I'm gonna put in here. And then the number of jumps or the denominator, right, of the fraction. So I think of that as either the number of jumps or the denominator of the fraction. That's gonna be my radical value. Okay, so I'm gonna take, which kind of makes sense because that's saying what times itself 3 times
Yeah.
gives me 2, right? And the cubed root of 2 is what that is. So I don't know exactly what number that is, but I know that it's the cubed root of 2. So now we have to figure out how to put that into our calculators. So some of you guys have, like Sam, it was actually interesting that you asked that question. Is it the x radical button? You're gonna use that value and put a 3 in there for x. On a calculator like mine, Tayson, I'm not sure about yours.
Mine, I shall figure it out at some point.
Okay, so what I would do is actually on a calculator like mine, I don't have that square root key with an x over it. So what I have to do is I have to do 2 and raise it to the 1/3 power. So I will go, and the way I do that is with a little caret key. So I would do 2, and then there's the little caret key.
What if I just have a 3 and then the square root, like, and then you just put the 2 in there?
That will work also, yes. And then on mine, I have to open parentheses and do 1 divided by,
Okay, mine's
3.
located in a funny place, but it does have it.
Okay.
So what did you get?
Oh, do that one. Okay.
I just want to make sure I did it.
So I got 4 times 2 to the 1/3, and I got 5.03 ...
Yeah.
Okay, awesome. So then I'll multiply that by 2 to the 1/3, or the cubed root, like you guys are doing.
And then, oh, I think it's right.
So I got 6.34 ... times 2 to the 1/3 power. Oh my gosh, exactly 8. There we go. So I'm multiplying the last term each time by 2 to the 1/3. So when I do that, I'm just gonna go ahead and,
If we have a test and you're going to ask us what the
Is this-
1/25 is of something.
Is this gonna be like on the test? Like this kind of problem?
Maybe.
I'm gonna skip.
wow, just skip that straight up? No. It'll have this idea, but we're gonna continue working with this and try to solidify this idea before the test. Because remember, this is lesson 1 of module 3, right? So we've got a hot minute before the test comes around. Okay, and then it goes to, also on my calculator, when I'm hitting enter, because the last operation I did was times 2 to the 1/3 power, or times 2 to the cubed root of 2, or excuse me, times the cubed root of 2. When I hit enter, it just continues doing that. So I'm actually just getting all these values listed for me, which is kind of nice. So that's 20.15 ... 25.39 ... and 32. Wow. This is very exciting. I'm excited. Wow. There we go. Okay. So let's go ahead and answer these next couple of questions. 7, 8, and 9. These are our last few questions.
Yay.
Wow, even with all these technical difficulties, we're still thriving. We're nearly done. 7.
Teachers and students, excuse the interruption. We are trying to do a servicing activity on our server, and by virtue of that, we need to reboot items in our server room. This will disconnect you from the internet.
Okay, let's real quickly finish this so that hopefully it can keep recording. What number did we use as a constant
You're fine.
to complete the table? Oh yeah, because I've got a HDMI.
HDMI.
W.
Screen recording hardware. So you
Hi,
can
So they're
Sorry.
repeating it.
Oh,
They're
sorry.
like you can literally just turn off the
Copy
internet.
and
It
paste it,
doesn't
man.
change anything. I mean, it won't sync anywhere other than the iPad, so don't lose.
Well, I don't want it to sync. I like when it floats.
We use
Clearly a fan of the Titanic.
the square root.
So, what number did we use as a constant factor? You said the square root of 2? Yeah, and that we can just like, I like doing the square root. I like doing the square root of 2, but then also writing the 1.414, and then let's just put an ellipses at the end of that too to say it was an irrational number that keeps going, right? How about in problem number 6? What did we use?
The square root of
We use
3.
the cubed root.
The cubed root of 2.
Yeah, same thing.
It is not the same thing. Just
Because you're
gonna say it's not the same as the square root of 3. Okay, not that one, but the cubed root of 2. And I am glad that you said that though, Mia, because I do really carefully want to make that distinction that the cubed root of 2 is a different value. Okay.
You can write the little 2 in front of the squared if you really need, because then you can.
Yeah. Here's another way to think about that. That jump of 2, or the number.
That cancel.
The 2 jumps comes right here. Oops. 2 jumps comes up here. 3 jumps comes up here. Okay. This is the multiplier. Like the whole number multiplier, actually. Whole number multiplier.
Is this like what's gonna be on our homework
Multiplier,
assignment?
multiplier would be f of 1 over f of 0, right?
Yep. Okay, so let me move this all down actually. So then the cubed root of 2, which what is that value? Let's see. 2 to the 1/3 power. It's 1.2599 dot
We
dot
should
dot.
just go 1.26.
Well, I want to leave these ellipses so that I recognize that this is irrational.
Or yeah, that's what. Yeah.
That's why I'm not rounding though. Just so you know.
Oh yeah.
You can write little squiggly lines too, and then you can round it, and that would, like, as in instead of equals.
Oh yeah, that I like that, Tayson. That is a good adjustment.
What did you say?
It mean is, it's like approximately instead of equals.
Oh, a little squiggly.
Because then that would imply an irrational value anyway, just because, you know.
Correct. Yeah, very good distinction. Okay, and then give a detailed description of how you would estimate the output of a value f of x for x equals 5/3. Any ideas?
You would take the cubed root of.
Well, there's 3 jumps.
Okay, so we know there are 3 jumps.
You take the cubed root of f of 1 over f of 0.
Cubed root of f of 1 over f of 0, but how do I get the 5 in the numerator?
The 5 in the numerator would be if you repeat that 5 times. So you would just 5 times.
Okay, so the first one is, right, the function is 4 times 2 to the x. So I could say if x is 5/3, I could just do 4 times 2 to the 5/3. But we're not really familiar with this notation yet. So what we are familiar with is the cubed root of 2. We just kind of learned about that today. And there are 5 jumps then. So we could do 4 times the cubed root of 2 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 times the cubed root of 2. Right? Because now there are 1, 2, 3, 4, 5. I hope that's not a copyright infringement.
Hmm?
It was a song that I just started singing.
How many lines was it?
Well,
Two?
I'm monitoring
1, 2, 3, 4, 5.
Okay, yeah, they can't
Oh,
copyright
okay.
for
I
that.
will say, I don't think you matched tone accuracy enough for any system.
Wow, I'm offended.
And it has to be more
Sheesh.
than one line.
And it would have to be
Oh.
monetized.
I don't know the next line, so we're good. Oh, you don't think I'm making bones off this
First of
video?
all, you have like
Brother.
12 subscribers. You need like 1,000.
I don't think I have any subscribers, actually. Let's see. Are you gonna go subscribe?
Yeah.
Oh my gosh, my number 1 subscriber! Let's go!
Chasing nothing.
Bruh,
OG subscribers,
number
you two.
for life. Wait, I actually have one of your videos bookmarked, so I might get
Oh my gosh.
Yeah, you
Why
probably
do you
will.
have it bookmarked?
You get the atomic number and isotope tutorial.
Why?
Oh, I have to scroll through so many channels.
Mm.
I'm
Oh, wait, I may actually
subscribed.
already
Well, you
be
have
subscribed.
17.
Oh,
Why-
wow. Why do I have 17 subscribers?
You'll have 19.
I'm
No, they
already-
both were already subscribed.
I was
Yeah,
already
Oh, really? I
subscribed.
haven't subscribed.
What?
Like,
William.
we have a YouTube channel.
Who does?
Like my dad.
Nice. All right. Also, this lecture is done. Thanks for coming to my TED Talk.
Wait,